what I would suggest is going to tools that we have, such as SPSS. So I have an example here. I have a data set, and it's a similar question. We're going to look at, we have blood pressures by different regions of the country. So what you do in SPSS to get non-parametric tests is you select Analyze, go to Non-Parametric Tests, click on Legacy Dialogues, and click on the chi-square. I'm going to put region into my test values here. If I expected them all to be equal, that was my hypothesis, then you can do all categories equal. If I expected some variation on that, I can actually click on values here and actually put in the expected frequency by percentage, by decimal place of each of those. I'm going to click OK, and here are my results. So I have what you have here. These are the actual observed frequencies of participants in each part of the country. This was the expected. This is literally just the total divided by the number of categories. And it comes up with a chi-square number. It calculates degrees of freedom. It's the number of groups minus 1. There's 7 different regions. So I have a degrees of freedom of 6. And my sig, my p-value, my probability is 0, or 0.0. It's not completely 0, but it's 0.000, which means by definition it's going to be less than 0.05. Okay, so if we went back and did our, so we could do the same thing with our little analysis of our time zone regions. You can also calculate a chi-square using Excel. If you're not familiar with Excel, and I'm gonna make this larger so you can see it. If you're not familiar with Excel, what you can do is you go to the Formulas tab, and if you're not sure what you're looking for, you can click Insert Function, and you could even type in, like the start of the name, and then all of these, and you can actually look at different examples here. So what we're going to do, so we had 11 in the East, 8 in Central, 2 Mountain, 2 Pacific, and 3 International. And I didn't do the math here, so 26 divided by 7. So 3.7. Okay. So now if we want to do our chi-square, I'm just going to go recently used. I have actual, and I have expected. And you can see it's very tiny on the screen here, but our p-value is very small, certainly less than 0.05. So we do have a significant variation in our time zones in our little fictitious example here. All right, going back to my table. So if you use a chi-square, there's some other types of analyses you can use based on that. So for my public health colleagues, a lot of times we would do an odds ratio and also a relative risk ratio. Those are also using 2x2 tables. They're also using the chi-square as the statistical test that they're performing. If you're in other disciplines, you may have similar use cases where you'd use a 2x2 table. Again, what you have are exposure, yes and no, and cases, yes and no. So again, in my smoking to lung cancer, it's the smokers that had lung cancer, the smokers who didn't have lung cancer, and then the non-smokers who developed lung cancer and the non-smokers who didn't develop lung cancer. And what I do is I actually, literally put in A, B, C, and D for these 4 points in the 2x2 table, and then I go back into Excel, show that in a moment, to run the calculation. So if you're performing an odds ratio, so you're looking at the odds of observing the outcome in the exposed versus the unexposed group. So the equation for that, here we have the odds ratio, same thing, A, B, C, and D. We have an example here. Okay, so we have numbers in here, and this is the formula. A divided by B over C divided by D. And what I do then is go back to Excel. So again, I literally just set this up one time, and then I put in, I have all of my calculations right in here, and you can calculate your odds ratio and your relative risk simultaneously, actually. So here's my formula. So 40 and 10, 29 and 21. And from my worksheet here, that's exactly what I got here. And I have an odds ratio of 2.897. Relative risk uses a slightly different formula. It's noted here. And the relative risk in this group was 1.8. And here we go. So I have my odds ratio 2.897, relative risk 1.8. So an example here, once you get the math right the first time, test it, then you don't have to worry about these formulas again. Just go back, use Excel or use SPSS and let the programs run the math for you. Okay, so now we're going to go on to the some other non-parametric tests, the MannWhitney U Test and the Kruskal-Wallis test. When we're looking at independent samples and wanting to do a non-parametric method, we can use the MannWhitney U if you have 2 samples and the Kruskal-Wallis if you have more than 2. So the MannWhitney test then is basically the non-parametric counterpart to the independent samples t-test. And what we're doing really is we're comparing the medians instead of the means. So here's an example. I have a small group. I have 10 participants, 5 are intervention, 5 are placebo. Let's just say this is a new drug, and we're looking at the frequency of side effects. So what you do with the MannWhitney is you order them from the lowest to the highest. So from the number 1 all the way to the number 12. And then what you do is you have to basically settle the ties. So if you look in the 4th column, both there was a 4 and a 4. So you have to, that's the 4 and the 5 in the rank. So 4 and 5 is 9 divided by 2. So it's an average rank of 4.5. The same thing when we get to the 6s. You break the tie, so they both get 7.5. So there's the rank goes from 1 to 10 in that case. So what you do then is you have your formula, and again, relatively complicated formula, and the result is, in this case, for the group 1 it's a 3, the group 2 it's a 22. You always use the smaller of the 2 numbers. Let's see what that looks like using SPSS. So I have a non-parametric sample here. To do a MannWhitney U test, go Analyze, Non-Parametric, Legacy Dialogues, and if you look down here you have 2 independent samples. All right, so I have, again, the number of episodes, and I'm going to do Program. And because I can only use 2 groups, I'm just going to compare group 1 to group 2. Click Continue. I'm going to select MannWhitney U. Click OK. And if you notice here, I come up with the same results. My MannWhitney test is a 3. And here's interesting. Literally, whether it's a 2-tailed or 1-tailed determines whether you reject the null. The 2-tailed sig is 0.04, which is less than 0.05, and the 1-tailed is 0.056. So your hypothesis testing here is critically important in making that judgment. The next one is the Kruskal-Wallis test. This is where you're comparing 2 independent samples, or with more than 2 independent samples. So you have This is the non-parametric counterpart to the analysis of variance. Again, here's the formula. So what you do then is you have a sample. Again, you rank the sample from lowest to highest. And so you convert the numbers to their rank scores. So the lowest score was a 159. That's rank number 1. The highest score was a 215. That's rank 20. And then what you're doing is you're actually summing the ranks for this, and we come up with our score. So again, what does that look like in SPSS? Analyze, non-parametric, and this would be K independent samples. So here again, we'd put our episodes and our grouping variable. Have to define the range. There are 4 regions, so it's 1 through 4. And click OK. We had the Kruskal-Wallis selected there. And so in fact, with all of those numbers, we come up with a sig of 0.045. So less than 0.05, we would reject the null hypothesis. What if we have a matched sample test? So we can do the Wilcoxon signed rank, or we can do simply the sign test. So what we have here are pre and post values. In the sign, you're literally just taking the difference. So the pre minus the post gives us a score of 10, and that's a positive. And then you literally just rank them. The Wilcoxon also takes into consideration the magnitude of the difference, not just whether it was plus or minus. So, and again, it's a little bit more powerful or a little bit more sensitive than the sign test. So how do we do that? Again, analyze, non-parametric, legacy, and again here we have related values. So in this relatively fictitious data set, I have a before and an after, and I have the Wilcoxon selected, and also I'm going to select the sign. Click that, and so here's again the selection of tests can be vitally important. The Wilcoxon is taking in the magnitude of the ranks, okay, and we get a p-value, a sig value of 0.049. We're rejecting the null in this case. The sign test is just looking at the negatives and the positives, and we get a p-value of greater than 0.05, 0.289 here. So again, the Wilcoxon is a little bit more powerful, but again, sometimes you may only be able to use the sign test. So either of them will work. You just have to kind of think ahead before you run the test which one you want to use. And that brings us to the last one, which is the survival, or I call it the time event, because it's not always looking at death rates. We can look at other things as well here. Again, we'll go back to SPSS. I'm looking at, I have again some data here on readmissions. The way you do this, click Analyze, and go to Survival instead of non-parametric, and we're going to do the Kaplan-Meier. In my data set here, I have days. That's my time interval. I have readmitted as my factor, and the program will be my status. And so I'm looking at group. I'm going to look at group 1 here. Continue. My compare factor, I want to do a log rank, and I want to do a linear trend analysis. And so what you come up with is you have your survival tables, and then, oh, and I didn't do, The one thing I forgot to do, everyone wants to see a plot with a Kaplan-Meier, so you have to create a survival plot. And we rerun this. And now we also have our survival plot here. We don't have a significant difference here. It's 0.076. What does this mean? It means nothing in this data set because it's all kind of fictitious data. But if you were looking, if this really was, mortality rates or readmission rates, you'd be comparing, the control to the intervention group, for example.